Well, welcome back to the next installment in the Advanced SQL lecture series. This one is a biggie. So what we are talking about now, the so-called compositionality, is really instrumental in writing larger, more complex advanced SQL queries. And without compositionality, no lecture advanced SQL actually. So let's see what's going on there. It's quite interesting and quite important. Okay, so compositionality, or as one can put it, subqueries instead of values. That's actually a very big idea. Compositionality is a very fundamental principle of language design, actually in computer science, and well, a two-liner that explains the principle, the basics of compositionality, the fundamental idea would be: the meaning of a complex expression is determined by the meaning of the constituent expressions, so of the parts of the expressions. And that may sound obvious to you, but it's really a big deal, because it means I can build up complex query expressions by assembling tiny, simple query expressions that I can test in isolation, and I will see, hey, this tiny expression yields value 42. That's cool, because I then can use this tiny expression in the context of something larger, of a large advanced query, for example. And inside the context of that query, the meaning of the simple tiny expression will still be 42. I can rely on that. There will be no side effect or no context dependencies. The meaning of such a tiny expression contributes to the meaning of the entire big thing. And that allows us to assemble complex queries from tiny individual parts that we can test in isolation. It has not been like this all the time in the SQL language. So with SQL 92, and then for in particular the SQL 99 standards, SQL has gained compositionality. So this big idea now applies to SQL in a way that makes it feasible to really write complex, large queries, and we will try to do that and exploit that in this particular course. Okay, so cutting this down to what that means in for SQL. Well, that means wherever we expect a value v, in a query, that may be a tabular value or a scalar value, so just an atom like an integer or a text value or a boolean, for example. Okay, so wherever we expect such a value v, we can write a literal v to specify this value v, but we could also specify an entire subquery. An entire SQL subquery of arbitrary complexity, as long as we enclose that query in parentheses, it will be evaluated, it will yield the value v, and it will then be just like the literal that we would have specified in place. So specifying the literal 42 in the place where we expect an integer, or specifying a very complex query in parentheses that computes 42, is the same thing in SQL. Okay, these queries in parentheses that I was mentioning are also, as I call them, termed subqueries. So subordinate queries that contribute to a larger whole, to a larger entire advanced SQL query. Okay. Such nesting queries in parentheses, such nesting may occur to arbitrary depths. So a subquery may contain another subquery, which then contains another subquery. This allows us to build a whole hierarchy of subqueries, a whole stack of subqueries that are all evaluated as we expect them. If such a query yields a value v, it's okay. So we can compose queries to build up larger things, larger query structures in a way. In SQL, this actually goes a bit further. And And there are some conventions that make it very simple and very practical, very pragmatic to really assemble complex queries from simpler parts. And one of these helpful utilities in SQL is the fact that whenever we generate or whenever we execute a query, a SQL query that yields a single row, single column table. That's what SQL queries do. They yield tables. But in the particular case that the query yields a single row, single column table, so a table of this shape that contains a single cell that holds the value v. In such cases, the entire subquery that computes this single row, single column table is as good as the value v that is held in this particular single cell. So wherever we expect a single, say, integer, we could specify an entire arbitrarily complex SQL query that yields a single row, single column table, having a single cell, holding an integer. We could put this query in parentheses and use it where we were expecting such an integer. So we could compute such integers from arbitrary complex expressions, SQL expressions, and use them to build a larger query. There is some convention to that and some rules. So should the query that we are using, the subquery that we are using to compute this particular value v, should it yield an empty table, so a no row single column table, then the query interprets that as if v would be null. So an empty table used in the place of an atomic value, a so-called scalar subquery in parentheses, would be interpreted as null if the table that is computed by the subquery has no row. If it has more than one row and thus more than one cell, which of these cells should be picked to be the atomic value that is being computed here? The first value, the second, the last value, whatever. The answer of SQL in this case is the query will be stopped with a runtime error. So at runtime, when we find out that the subquery that should compute a single atomic value actually computes a table of 2, 3 arbitrarily many rows, should we detect that at runtime, the query will be stopped with a runtime error. So really make sure that the subqueries that are supposed to compute a single atomic value really yield a single row. And the same applies, of course, to the number of columns. We really need a single column, single row table in this case to specify a single cell. Anything else, more than one row or more than one column, will yield a runtime error because we cannot unambiguously extract a single cell value v from the result of this subquery. Let's see, I brought such a SQL query with me. Let's see what that does. So you see that this query, this select clause, tries to perform some arithmetics on integers. So 2 plus something. Clearly, what we need here on the right-hand side of the plus value is some numeric value. That's fine. We could specify literal here, like 40. But we could also specify a subquery in parentheses, and that's what I'm marking here. This is the subquery in parentheses that I've placed here. It could be an arbitrarily complex query. In this case, this subquery is consulting our playground table T, looking up the row in which the A value is 2, and in that particular row, it will extract the D value. The D value, if you recall, the D column specifies or holds integer values. That looks good to me. So this is a single field or a single column row that will be extracted, and it holds integer values. This predicate will admit at least or at most one row, because as you recall, maybe the A field in the T table is a key. So this predicate will be true for at most one row. Maybe no row, maybe no row, then this will be the empty table, and the rules of SQL say this scalar subquery in round parentheses will then be interpreted as null. Okay, but in the good case, this will admit exactly one row, and from that exactly one row we will extract exactly one column. So this subquery in parentheses will yield a single column, single row table holding some integer value, and that value will be extracted and then treated as a simple integer value, and then be used in the addition to this literal 2 here. Okay, so let's see what comes out of that. And the answer is 42. Hey, yeah. So let's check the table T and its contents again. So we were looking for the row with a value 2. That's this particular row. There's only one row of that. A is key. And the D value here is 40. Yeah, exactly this D value has been extracted and then used as the right-hand side in this addition. And the answer is 42. Because this is a subquery, it could also be evaluated on its own. So let's take this guy and only evaluate this piece, the subquery piece. Let's put that here, copy it here, and then add a semicolon. All right. And yeah, okay. That's a single column, single row table containing just the 40. This is the result of the subquery. The 40 is being extracted, treated as a simple integer, and then added to the 2 above here. That's fine. You can see that I'm specifying a very strange column name, in this case an underscore in this case. That's because when we extract the cell value out of this single row, single column table, the actual column name, the actual field name is really immaterial, and anything could work here. I'm using the underscore in such cases to document to the query reader that the column name really adds nothing here, contributes nothing to the meaning of the query. Anything would go here. Okay, so let's see what happens if we modify this predicate and then, for example, find those rows in which the a value is 0. And let's scroll back to the T table. There is no such row. So the result of this subquery will be the empty table. The empty table, and the rules of SQL say the empty table is interpreted as null in this scalar subquery context. So what we are effectively evaluating here is 2 plus null. 2 plus something unknown will be unknown. The whole result will be null. And there you go. The answer is null. Okay. And the really bad case is if this predicate admits more than one row. So there is more than one row in T that it has a value larger than 2. There's actually 3 such rows. So this will yield, let's evaluate that on its own. This subquery will yield a single column table, that's fine, but not single row. It has 3 cell values here. Which of these should be picked to be added to the 2 here? And the rules of SQL say, no, that's an invalid query at runtime. I will see that this subquery yields too many rows, and the entire evaluation of the entire query will be stopped with a runtime error. So let's do that. More than one row returned by a subquery used as an expression, and I think this error message is quite readable and makes sense. In general, the error messages produced by SQL, by PostgreSQL, are quite useful, and I think it really is clear what's happening here. So let's quickly switch back to the good case, and we are safe again. Okay. Everything we've just played with in the editor is also documented on slide 17. Okay, so the idea of scalar subqueries they also extend to the notion of queries that compute entire rows. So any query, any query that computes a single row table with n columns could be used in place of a row value of n fields. Okay, so the n cell values v1 up to vn, they make up a row value. The field names of the row values are the column names of the tables that we are generating here. This makes up a perfectly valid, a perfectly fine row value of with n, and it could be used anywhere where such a row is expected in an enclosing larger query. Okay, so the same ideas apply here. An empty table, again, is interpreted as a null value, and we know how a row value that is null is actually to be understood. This is a row value consisting of n fields containing only nulls. Okay, that's the interpretation of an empty table returned by such a subquery. And it should be no surprise that a subquery that yields more than one row is considered to be a runtime error. Okay, so because which of the rows that have been returned here should be picked as the one single row value that we are needing here. Okay, so such a query would be stopped and then halted by yielding a runtime error. Okay, so with subqueries, we now have more than one query in hand. We have the enclosing top-level query, and we have the nested, in parentheses, the nested subquery. How about the visibility of row variables? How about the visibility of row variables that are bound in the enclosing query and the visibility of row variables that are bound in a subquery? Such rules are called scoping rules in programming languages. And the SQL has scoping rules, and they are not surprising. Excuse me. So how about row variable scoping in SQL? Well, any row variable bound in the enclosing query. For example, in the from clause. From clauses are where row variables are introduced. This row variable t is bound to the rows of t. Any subquery that is nested inside this enclosing query will see the row variable t. So inside this subquery, we would see the binding, we would see the row variable t, and we could access its binding and work with the bound value here. So that would be considered fine. Passing bindings from the enclosing to the subquery is considered okay. Bindings that are established inside the subquery are visible inside the subquery according to the rules of SQL, of course, but they are never visible outside in the enclosing query. So bindings never escape the subquery and then are visible in the top level enclosing query block, for example. That's forbidden, and the scoping rules say they only promote bindings inwards, so towards the subqueries. From the viewpoint of this subquery here, note that we can access and work with this row variable t, but inside the query text here, inside, nowhere would we find the binding side for t itself. There is no from clause inside the subquery that would bind the row variable t. That from clause is found outside. So from the viewpoint of this subquery, this is the variable whose binding side is actually invisible to us. T is just there, it's just in place. In programming languages, such variables are called free variables. So t is indeed a free variable that is visible inside this subquery. Okay, so notions and ideas of variable scoping and variable visibility, they apply in SQL and to enclosing and subqueries, just like you are probably used to in your favorite programming language. Let's see what that means. Let's see what that means, that a nested subquery, can actually see and refer to the bindings of variables that have been bound on the outside in the enclosing query. That would be such an example. Of a query. Okay, so we've got the enclosing query. This is the enclosing query. Okay, here. All right. And there's a particular spot in the enclosing query where we are expecting textual value. If you recall, the B column carries textual values in our playground table, and this inequality comparison expects textual value on the right hand side. And we are using a subquery. To compute such a textual value. So we expect this subquery here to compute a single row, single column table that holds exactly one textual value. Let's see whether we can expect this query to do just that. Well, we are looking at the playground table. This is a predicate. On the key column of the playground table. So this will yield at most one row, this equality predicate, and from that at most one row we will extract exactly one column. So that looks good to me. That should yield a single column table with at most one row. So no runtime error here. That's fine. Okay. From the viewpoint of this subquery, this T1 here is not bound inside the query. The binding side lies outside the subquery, so T1 is a free variable from the viewpoint of this subquery. Somebody else supplies some bindings of T1 for us. And somebody else, of course, is the subquery. This is the binding side. Okay, so from the viewpoint of the subquery, this is going to be evaluated multiple times for each binding of T1 supplied here from the outer side. For each binding of T1, this subquery is going to be evaluated once. Sometimes, or at one time, T1 will be bound to this particular row, and for this binding, we will evaluate the subquery and see whether the predicate is true and so forth. Another binding for T1 will be produced, this binding, then this binding, then this binding, then this binding. For all of these bindings, we will evaluate the subquery here in parentheses, and see what B value we can compute for this particular subquery. Okay. Another view of such a subquery with free variables is that of a function. It's this subquery with a free variable behaves like a function. You provide a T1 value, a T1 argument, let's say. From that argument, I will perform that query and return a result for you, namely this B value in the single row, single column table that I'm computing for you. Okay, you provide a T1 binding, a parameter, a function argument in a sense. I will provide a T2B result for you and return that as the result value. So this subquery acts like a function of argument T1. This is what is meant in this primary paragraph here on this particular slide. The subquery is a function Q of one parameter T1 that will produce, for each T1 will produce a particular answer. The database folks wouldn't refer to this subquery as a function, but would refer to this as the correlated subquery, a subquery that contains free variables that cannot be interpreted and evaluated on its own. We need a T1 binding from the outside to make this a complete and valid query that we can then evaluate. So that's correlation, the mentioning of variables, of row variables that have been bound outside the subquery. Visibility is no problem. Bindings are propagated from the outside to the inside, so this binding should work just fine. Okay, so let's see. I have brought this example with me. Here you go. Okay, so this is just the query from the slide. This is our subquery. This is our subquery. And in contrast to the subqueries that we were evaluating in the example before, this query has a free variable. T1 is the free variable. Only if you give me a particular binding for T1, I will be able to execute this particular subquery. So just copying and pasting this guy on its own and evaluating it at the prompt here, that will give us a problem because nobody supplies a T1 value. The enclosing query with the binding side of T1 is missing. Just evaluating this correlated subquery on its own will yield an error. Okay, there's no from clause entry for table T1, so the row variable T1 is unbound. I cannot evaluate this subquery for you. In the context of this entire query, but the query makes perfect sense. We will enter the subquery once we know a particular binding for the T1 variable, and we'll thus see a particular valid result evaluated. When I evaluate this query, the result in this case for this particular example will be empty. Let's see. Oh, indeed, it's empty. This is not a runtime error. The result is just empty. And I encourage you to come to the Advanced SQL forum and explain to me why the result of this particular query has to be empty for any table T that we can, or for any table T that we can, or for any rows that we insert in this particular playground table T, the result of this query will always be empty. Please come to the Advanced SQL forum and post your explanation for this particular empty result. I'm looking forward to read your explanations and your rationales for these empty results here. I mentioned that for each binding of T1 here, there will be one evaluation for this particular subquery. And we could have entire lectures about clever strategies to evaluate this particular query, whether we really have to re-evaluate the subquery for each binding of these T1s again and again and again. Let me tell you, there's more clever strategies to evaluate the subquery, but the naive way, the straightforward way, is actually really this nested evaluation. Find the binding for T1, then evaluate this guy. Find the next binding for T1, then evaluate this guy. And we could actually have the system explain to us how it chooses to evaluate this very simple toy query for us. And how we do that is by prefixing the query with the explain keyword. This is one of the main tools that we're using in the DB2 lecture to look behind the curtains and the evaluation of SQL queries. We will very seldomly use it here in this Advanced SQL course, but for now, let's try that. Let's have PostgreSQL explain to us how it would go about the evaluation of this nested correlated query. Okay, so let me evaluate that. Okay, so let's see. Okay, so this particular query would be evaluated like this. We would read all the rows of table T and we would call them T1. Okay, so this corresponds to this particular from clause. While we scan, we would perform filtering. This corresponds to this particular where clause here. And the filter would make sure that the B value of the rows that we are currently reading is not equal to something that is computed here. Okay. And what's computed here is the subplan, the subquery that we have specified. So if B actually is not equal to the value computed by this particular subplan, then the filter would let this binding path, and we would evaluate the select clause here on the top. And if we look what subplan one actually does for us? Well, it scans over the rows of table T again, calling these scanned rows T2, and then again performing a particular comparison between the A field of these T2 rows and the A field of the T1 rows of the outer rows. This is exactly this comparison here. Okay, so the nested evaluation, find bindings for T1, then evaluate the subqueries for each of these bindings. You can also find this in the actual evaluation plan that PostgreSQL is choosing for this very simple query. Okay, so that's the semantics of nested queries, of correlated subqueries in SQL. Okay, a very important building block in producing and assembling larger queries. Okay, so much for now. Let's close this video. It's long enough. I will see you for the next edition and the next course video for Advanced SQL. Stay safe, stay healthy until then, and see you then. Bye bye.